Good afternoon, everybody. This is a joint work with Antonio Bonatti for the CNR and Professor Roger Carfagni from the University of Parma. Here we critically discuss the principle according to which lamination has always a beneficial effect from the safety point of view. Okay, by starting from the glass tensile strength that is governed by surface microcracks, which open almost exclusively in mode 1. That is why only the component of stress orthogonal to the crack axis is responsible for failure. This is why a dependence upon the state of stress arises. And because of the probabilistic nature of crack dimensions, size effect is characteristic for the strength of glass. Another peculiar aspect is that the subcritical crack growth, because of which cracks can grow in time, even for stress level much lower than the critical one. And then because of the manufacturing process, that is the float process, one side of the pane is exposed to air, while the other one is in contact with steam bath and steel rollers during production. That is why different effectiveness scenarios are present of the two surfaces of the glass, and this is why these are characterized by different statistics. And then because of the cutting, additional effectiveness at the border makes these the weakest parts of the glass elements, and even these are characterized by a proper statistic. Okay, it is a generally accepted principle that lamination always provides an improvement in terms of structural safety, but this is certainly true for materials who exhibit plastic capacity, while for glass, for brittle materials, this principle lacks of a theoretical justification. Now, here we will obtain the statistical distribution of strength exhibited by laminated specimens during an experimental campaign. So the actions are considered as deterministic action, where the load, obviously during experimental campaign, is precisely controlled and measured. In particular, we refer to two case studies. In the first one, we consider a laminated plate subject to coaxial double ring test, according to which the area delimited by the inner ring is approximately subject to an equibiaxial state of stress, which represents the most favored case, since this is the only case in which you have the 100% probability of finding a critical crack at right angle with the maximum principal tensile stress. And then for in-plane loading, the case of the 4-point bending, in which the edge between compressed between the 2-point load is subject to a constant maximum stress. And then I will investigate how the failure probability and the cumulative distribution for the strength can vary according to the number of plies into which the laminated glass pane is divided. So for what concerns glass strengths, the most used statistic is by far the two-parameter variable distribution, is even the simplest, but for the moment this is okay. Here M and eta are the parameter, are the shape and the scale parameter of the distribution, while sigma is a measure of stress. By assuming that the defectiveness is homogeneous and isotropic, so there are no preferential orientation for cracks. For cracks, we can write the failure probability in this other form, in which AF is the effective area that synthetically takes into account the effects of the state of stress and size upon the failure probability. Only in the case of equibiaxial state of stress, K is equal to 1, and so the effective area for the case of the coaxial double ring test is exactly equal to the area delimited by the inner ring. So to construct the cumulative probability function for the strength of the laminated plate, we adopt the failure mode approach, according to which we have to investigate all the failure modes, according to which a redundant system can fail. A failure mode is defined as a series of plies that fail, so that the whole structure reach a limit state. And according to the failure mode approach, the failure probability of a laminate is given by the union of all failure modes, where the failure modes is given the product of the probability that the event failure of the specific ply in the specific failure mode occurs. Here, this term, PFJI, is given by the two-parameter variable distribution. So we do not go into the detail of the analytical treatment, but we use the event tree representation that is a synthetic way to illustrate how a redundant system can fail. Obviously, the shear coupling, to what extent the plies can transfer shear strength strongly affect distribution and redistribution of stresses after partial failure. We consider here two limit conditions of layered behavior. So in this case, there is no shear coupling among the plies, and monolithic behavior in which the shear coupling is full. Here, if we observe the case of the sound state, the case 1, here, if we neglect the thickness of the interlayer, the three plies in this case are equally stressed, and so the probability that the first ply, the failure of the first ply does not occur is exactly equal to the probability that none of the three ply fails because of sigma maximum. And hence, here we have that the effective area for the failure of the first ply is 3 times the effective area of a single ply pane. This represents the negative effect of lamination, this increasing of the effective area. So, to what extent the ability of the laminated plate at redistributing stress can counterbalance this negative effect will be discussed later. But this is a negative effect that probably has never been taken into account. Differently from the layered behavior, for which it is always possible to construct event trees that are characterized by only one failure mode. In this case, the case of monolithic behavior, the more are the number of the plies, the more complex becomes the event tree. In this case, we have two failure modes, since the lower ply is the most probable to be the first that fail. But there is even a not null probability that is the intermediate ply to fail first. Even in this case, we have an increasing of the effective area, because the first ply can fail at the lower surface, at the lower surface or at the upper surface, while only at the bottom surface can fail the intermediate one. Here, the increasing of the effective area is, although it is much more limited than in the case of layered behavior, we have this negative effect even for monolithic behavior. Here I recorded the so-obtained cumulative probability function for laminates composed by 1, 2, 3, or 4 plies. For layered behavior, it's evident that for most of the distribution, the strength of the single ply pane is higher than the strength of laminated plate. While only in the very left-hand side tail of the distribution, the ability of the laminate at redistributing stress can counterbalance the negative effect given by the increasing of the effective area. If we refer to the 5% quantile that is generally associated to the characteristic value of strength, we can see that for layered behavior, the 5% quantile of the single ply pane is much higher than for laminates, while for monolithic behavior, for the 5% quantile is slightly lower, and then in this case, lamination is positive for the 5% quantile. Anyway, we can claim that it is not true that lamination leads to an increasing of the 5% quantile of the distribution in all cases. Then, Obviously, during the lifetime, glass is subject to static fatigue. That here we have, since actions are generally schematized as lots that remain constant for a certain characteristic in time. Here I constructed again the cumulative function for the strength for the coaxial double ring test of duration 6 months. It is evident that there are not, by comparing this function with that associated with the inert strength, there are no qualitative difference, even though in the case of 6-month duration, the domain in which the strength of laminates is higher than the single ply plate is smaller than in the case of inert strength. Then, by passing to the case study 2, the in-plane 4-point bending, what is the best statistical model to interpret the edge strength is still a matter of debate. So now we use the most common approach, that is consists in considering again a statistical variable, as in the case of surface strength. Two are the more common approach. One is to consider that the edge strength is not dependent upon the thickness, but it's only dependent upon the edge length. And another approach is that the size effect is related to the edge area here shown. I've used again the Fowler mode approach for obtaining the cumulative distribution for strength. But what is of interest to observe here is that if the size effect is related to the edge area, lamination does not affect the edge area. And this is why, in this case, the effective area of a laminated plate is exactly equal to the edge area of a single ply pane, and hence the ability of the plate at the redistributing stress can certainly increase safety of the element. While if the size effect is related to the edge length, the situation is very similar to the case of a coaxial double ring test with layered behavior, in which the effective length is n times the effective length of a single ply pane. In fact, the distribution, the statistical distribution for strength, the cumulative functions are not different from the qualitative point of view, with the function valid for CDR test with layered behavior, in which only in the left-hand side tail of the distribution, the strength of the laminate is higher than the strength of the single ply pane. I try to consider even the probability that collapse starts at one of the external surfaces here, but yeah, the results are almost the same, so it's clear that this is possible to neglect the probability that collapse start here. We focused the attention of the cumulative probability function for strengths of laminates. Obviously, we have derived this function by considering deterministic action. If one wants to evaluate the structural safety of a laminated glass element, cannot neglect the probabilistic nature of the action. In this case, so we have to make the statistical convolution of the density function for the effect of the action, that is Fs, and the cumulative probability function for the laminate strength, that is the one derived through the Fowler mode approach. It is important to notice that the Fowler probability that are considered acceptable according to the Eurocode for structural elements are very small, of the order on 10⁻⁵, 10⁻⁷. Here, just to illustrate, I record a potential probability density function for the action, the cumulative function for laminates composed by n plies, and with the black line, the cumulative function for laminates composed by n plus 1 plies. Here, the red area represents the negative effect of the lamination, while the light blue area, the positive effect of lamination. Obviously, it is not correct to directly compare this area. So this area can be directly compared only if we have the same probability of reaching any stress state. Hence, if the density function for the action degenerates into an horizontal line. In this case, if the blue area is higher than the red area, it's convenient to continue splitting the element into plies, while vice versa, if the red area is higher than the blue area, is not convenient. For the deterministic action, this density function degenerates into a vertical line. In this case, if this line intersects the blue area, it is convenient to continue splitting the plate, while the contrary is true if it intersects the red area. While in structural design, obviously, the red and the blue area are weighted by the probability that the stress state reach the value associated with the blue and the red area. In particular, the more the peak of the density function is on the left, the more convenient will be to continue splitting the pane into plies, and vice versa. Obviously, this work is a work in progress. The main idea, the main scope of this work is to lead to an optimization of the use of the material glass into laminated solution. And among the most well-known standards, only the German DIN provides a coefficient that take into account the effect of lamination upon structural safety. And it provides a coefficient that increase of 10% the characteristic strength of glass if laminated solutions are adopted. This standard is the only one. But in our opinion, it would be useful to use a coefficient that must multiply the material partial factor for the safety factor, that must be calibrated on a statistical basis by considering the target filar probabilities considered as acceptable according to the Eurocode. Here I present some results, partial results, obviously. This is a work in progress, in which this coefficient is calibrated on a statistical basis. It is evident that the coefficient should be related to the class of consequence. Different value of KL are reached for the different class of consequence. And if we observe this graph on the left, that refer to vertical facade subject to wind load and to a target failure probability of 10⁻⁴, we can notice that after a certain number of plies, it is no more convenient to continue splitting the element into plies. For example, a 20 plies pane is not safer than a 3 plies pane if we refer to a target failure probability of this type, while this effect is less marked for elements in class of consequence 3. And when we consider horizontal roof under snow load acts together with the self-weight, that is almost deterministic action. In this case, this effect is not appreciable. It's much less pronounced. Hence, in conclusion, to conclude, it is questioned the principle according to which the effect of lamination upon structural reliability is always beneficial. Certainly, this is always true only for the very inside tail of the distribution. The 5% quantile of the laminate strength distribution is not higher than the 5% quantile of a single ply pane in all cases. And if we consider the case of the German DIN that provide a coefficient equal to 1.1, probably according to these results that are only partial for the moment, probably is even too much conservative in most cases to use 1.1. Obviously, here we have KL here and not multiplied by the characteristic strength of glass. So indirectly, they use a parameter KL equal to 0.9. Here we have coefficients that are, in most cases, lower than 0.9. We have noted that static fatigue only slightly affects laminate strength distribution. And for what concerns edge strength, lamination would be always positive if the size effect is related to the edge area, while the same is not true if the size effect is related to the edge length. Thank you for your attention. Oh, yeah. Maybe, yeah, okay. Maybe during question, I can say something about size effect in glass. Okay, now what I want to say that according to the Fowler mode approach, the way in which the size effect is analytically derived is crucial for the results of the analysis. Up to date, only the effective area derived by the two-parameter Weibull model has been proposed in technical literature, albeit for what is my knowledge. And probably to correctly characterize the size effect, it would be very important for the correct definition of the structural reliability of glass strength, and hence to optimize the use of the material. Thank you.
Thank you very much. Are there any questions?
Thank you. I appreciate the reduction in probability or increase of probability breakage by using a multiply laminate.
Yeah.
But in terms of the title being about safety, certainly having multiple laminates has redundancy. Do you agree with that?
Yeah. When laminating, we have a positive effect that obviously is redundancy and is the ability at the redistributing stresses after partial failure. But we have even a negative effect that is the increasing of the effective area. So there is not a unique solution. The solution depends upon the case, upon the target failure probability. This is why here we have these two. Okay, this area represents the negative effect due to the increasing of the effective area, while the blue one is the redundancy. So we have two effects, one positive and one negative, and then we can evaluate the structural safety only by making this calculation, the statistical convolution of the distribution of strength and resistances. And these are the partial results in which you can say that by passing from a single ply pane to a two-ply pane, obviously we have an increasing of the structural safety, because the lower is KL, the higher is the structural safety. But after a certain number of plies, this value goes up. And this is why I said that if we refer to a target failure probability of this type, a 20-ply pane is not safer than a 3-ply pane. Obviously, these calculations are only partial, and that depends upon the analytical model that you use for describing the size effect. And at the moment, we are obliged to use the size effect derived by the two-parameter Weibull distribution because there are no other models today. And that is why at my institute we have designed and we are going to start with an experimental campaign that will be aimed at defining the size effect in glass. Okay? Thank you.
Any other questions? If not, thank you very much for the presentation.
Thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!